This course employs the book by Professor Robert Pierret, Semiconductor Device Fundamentals. All the explanation and also equations are based on this book. So please, if you're interested, please purchase this book and then listen to my lecture. Thank you. Okay, so you don't have the book today, but I'm going to cover 2 chapters of the book. And first chapter is a general introduction to semiconductor physics, and I'm just going to try to basically cover the basics of band diagram, or I will try to review band diagram, effective mass, and so on, and to prepare yourself for chapter 3 and after. So first of all, semiconductors are very often made of group 4 materials, group 4 elements in periodic table, and combination of group 3 and group 5, combination of group 2 and group 6, etc. So let's take the most well-known semiconductor, silicon. And silicon is group 4 material, so silicon has 4 outermost electrons. And we want to talk about energy band of the silicon in the next 15 minutes or so. So to do this, let's think about simple system like hydrogen to begin with. So if I take distance r between 2 hydrogen, and plot energy of such hydrogen, then if distance is far away, then it is actually, completely dispersed, separated, 1s, 2p, and so on. So you get the quantized states. But at some point, of course, when hydrogen at 2 atoms becomes closer and closer, at some point, electron bound to each hydrogen starts to see each other, and consequently, by the Pauli excursion principle, the energy of such electrons forced to become different. So at some point when it gets closer, at some point it becomes like this. Okay? So basically, as these hydrogen get closer, electrons start to see each other, so that energy level of 2 electrons expelled from each other, and then they actually get dispersed. Okay? And then this is the case for 2 hydrogen, but what happens if you have many hydrogens? If I have number n hydrogen, then this level becomes they are separated into n different states. N different states, right? And that's really the source of that's really the origin of bands in semiconductors. And there's always this lattice constant, equivalent lattice constant, at which hydrogen prefer to separate themselves. So at this particular lattice constant, you can see that 1s level takes the energy between this and that, and 2p level, or I just say s and p here, p level takes energy between here and that, and so on. So there's almost continuous band, but it's actually not completely continuous. It's dispersed. band composed of n levels in each S state and P state. Okay? So for the case of silicon, energy diagram looks as follows. So for the case of silicon, we have silicon in a diamond lattice. So diamond crystal structure is basically superposition of two face-centered cubic crystal. So there's one face-centered cubic crystal. And also, if I superimpose one more, face-centered cubic crystal, it looks quite messy, but what I'm just trying to do is that here there's a displacement D in between these two states. In fact, this displacement D is exactly one quarter of the place between here and this diagonal atom. So if I draw a line between this atom and this atom, divide them into 4, and then put one atom at this 1/4 point, and use this as an origin to form face-centered cubic, then you get superposition of two face-centered cubics, which actually represents diamond crystal. So if I define these two atoms as a pair, then such pair actually such pairs form face-centered cubic lattice. Such pair pairs form face-centered cubic lattice. Okay? So, in definition of Bravais lattice, I hope you have heard about Bravais lattice. In the definition of Bravais lattice, within this pair, which we call this is base, within each base, there are two silicon atoms with 8 valence electrons. Because within each pair, there are 8 electrons. Okay? And we'll see how such 8 electrons play a role in formation of silicon band diagram. So silicon, I'm sure you have heard, silicon, diamond, and so on, actually takes sp3 bond, mixed orbital. So it always forms such so there's one silicon atom, and it forms 4 bonds in a real space, 3-dimensional like this. Okay? And I said, why do we call sp3? It is composed of one pseudo S state and 3 pseudo P states. So there's one S state and 3 P states. So sp3 diagram actually looks like this. So I'm going to plot as a function of the K and energy. K is the, basically actually K is a vector. 2 pi over lambda with some, I don't know, R vector. Real space vector. And basically, or and well, I should say actually 2 pi over some unit vector. This has to be multiplied by some kind of a unit vector, vector with length 1, vector with unit length, and then band diagram actually looks like this. So this is energy versus reciprocal lattice vector K, and this part, S part corresponds to S part here, and P part, this part, P part corresponds to here. So there is S part and P part. In fact, P part is composed not only by one P, but actually 3P. So there's one S and 3P. And we know that each S, P, P, P is composed of not actually continuous line, but N points. So each line is actually composed of N points, right? Because there's actually N states in each state. And here, let me introduce a so-called spin, so that in fact, electron takes spin up and down because it's spin half. So for each point, we can put 2 electrons. So in fact, I can pack 2n electrons here, 2n electrons here, 2n electrons here, and 2n electrons here. Okay? 2n electrons here. And how many electrons do we have? In each base, we have 8 electrons. And real crystal, there are N bases. So each base, this is one base. And there are N bases in a crystal. So therefore, the total number of electrons is 8N. Okay? So there are 8 N available electrons. Of course, ignoring the inner shells. But in the outer shell, electrons that we can use to form band, there are a total of 8N electrons. And such 8N electrons try to fill the states from the bottom of the energy band, because electrons want to minimize the energy, right? So this is why 2n electrons go into this band, 2n electrons go into this band, 2n electron go into this band, 2n electron go into this band, and then we run out of electrons. So after filling all these bands, we ran out of after completion of filling this such top energy points here, we actually ran out of electrons because, there are already 8n electrons. By the way, you're welcome to ask questions if you have anything in between. Okay? And as you know, the energy this empty space in energy is called band gap. So we have all these bands completely filled up to here. And then there's actually energy gap here. And there are no electrons in such band. And very often, this is called conduction band. And this is called valence band. Okay, this is called valence band. Okay? And here I drew, this is energy gap, just for simplicity. But in fact, this minimum is actually lower than this point. So actual energy gap becomes like this. And this point is known as an X point in the case of silicon. X point, and this is towards 100 direction. So in fact, if I take a diamond lattice, then because it's cubic symmetry, I can define 100 direction, 111 direction, 110 direction, and so on, which I guess you will be working on your homework. And then you think about difference in periodicity in 100 direction, 111 direction, and so on, because obviously periodicity of atoms in different crystallographic directions is different. Therefore, energy band is different depending on crystallographic orientation. So very often we actually draw this way as towards 100 direction, and this way towards 111 direction. And we can also connect this part to 100 to 111 and 110 and so on. But details will be actually written in a textbook, so please refer to the textbook. So now you see, okay, in a reciprocal space, in a wave number space, we can actually pack 8 electrons into those 4 bands, 8n electrons, and then we ran out of electrons, and then there is completely empty band. And for electrons to move around, we have to take 1 electron out of here to bring it up to, let's say, bring it up to this point so that this electron can actually move around. What does it mean? What do I mean by moving one electron from here to here? It takes energy. What kind of energy do we use? Okay, that's simple. We have silicon crystal. Okay? From each silicon crystal, it represents that each silicon provides 4 outer electrons, and combination of all these, 4 each, brings it back up to such, 2 bonds between each pair of silicon, each neighboring pair of silicon atoms. You can see all electrons are used up for forming bonds, crystals. And this is why, this is a situation I drew here. All 8n electrons are used to fill up the valence band. Okay? Then, if I provide energy to remove one of the electrons, In fact, energy is exactly, for example, of this energy here. Then I can break the bond, remove electron from such bond, and make it free. Okay? Make it free. And such electron can move around. Such electron can move around. And there's actually empty space called holes. Okay? Empty positive space, point. So this is a situation where I made empty hole in a valence band, because otherwise the band is filled completely by electrons. So I actually made one positive hole here, and then I actually brought one negative electron into the conduction band. And this way, electrons and hole can move around freely. Good, it's clear. So once we have created such hole, when electrons, they can move around freely. In fact, they do move around freely. And the biggest energy that electrons and holes use usually are the thermal energy. So at 300 Kelvin, we have kBT, Boltzmann constant times T equals to about 0.026 electron volts. So electrons and holes use energy received from thermal environment to move around. They move around like crazy. We can also apply bias from outside. So we can actually apply to semiconductors, we can apply bias. Then electron and holes move around. They are moving around freely. So they are moving around, for example, this much and this way and that way and this way, completely randomly by thermal energy. So I'm drawing sphere here. Sphere of velocity. Sphere of velocity. So this is center, and I can draw Cartesian x, y, z. But basically, that's vx, velocity v, velocity y, and basically sphere. I'm drawing sphere because assuming that there's a velocity is constant in all directions, given by thermal energy, and they go everywhere. So it's a sphere. And then we can apply external voltage to the external. I can connect battery to such silicon, and for example, in y direction, this is y direction, right? Then if I connect battery in this manner, then such sphere is shifted slightly to the left, right? Slightly to the left, because electron shifts this way. Velocity shifts this way. And such shift is approximately given by EV. So this is 1.6 times 10 to the minus 19 coulomb charge of electron times applied voltage. So it's applied voltage here. So the velocity is slightly shifted to minus y direction, and this is how carriers or electrons generated by energy actually current goes through the single crystal of silicon. So by the end of this lecture, I will try to cover. This is actually quite difficult because you have never seen the book. And I'm trying to cover what is described in the book conceptually. There are equations in the book, so you can follow equations, but I'm just trying to provide you conceptual aspect of semiconductor, how band concept works in semiconductors. Okay? So there's a velocity of such velocity shift due to connecting batteries. Okay, and such shift. So by applying voltage, I said, how much shift do I expect? I said force is equals to, which notation am I using in a book? A book uses Q, so I should actually draw, this is Q, electron charge Q, minus Q E, minus because, so I should say actually electric field here, and QE equals to effective mass. So basically, to treat electrons, we want to actually just use simple Newtonian classical physics. It's just a simple force. Okay, I applied electric field from outside. How much force is imposed on each electron? We want to calculate this using classical physics rather than quantum physics. And the bridge between quantum, which is shown here, and classical over there, is basically the concept of effective mass. So effective mass, concept of the effective mass is introduced in semiconductor physics as follows. So here, the effective mass of the electron. So M, what M should I use? M star of electron. Effective mass. Mass of electron is given by M star equals to h square. It's a Planck constant. So this is a second derivative of energy versus K. So really, the curvature here defines how heavy or how light each mass is. And here we care about the curvature here, bottom of the conduction band. And curvature here is inversely proportional to the effective mass. So curvature, if this curvature is small, or large, which way you want to say, but if the curvature here is large, then effective mass is small because it's inversely proportional. So here, if the curvature is very sharp, large curvature, larger the curvature, smaller the effective mass because it's inversely proportional. This is small curvature. If it's smaller, then of course the effective mass is larger. Then, of course, lighter the mass, easier the electrons move around. So with same electric field, electron moves more because of this, small effective mass here. And then also, effective mass of the electron is this way. Effective mass of hole is this way. So effective mass of electron is larger than 0. Holes, effective mass is opposite. So this is hole. Effective mass is smaller than 0. This is electron because the effective mass is larger than 0. So let's move on. So now we have actually introduced the concept of the band, and very often we just draw in semiconductor device, we just draw valence band and conduction band. We do care about the curvature, but that's all. That goes into effective mass, and we can just treat them as a classical particle. So from now on, even though physics-wise this band diagram is important, we're going to draw energy band diagram always like parallel to lines. So that is just one horizontal line called valence band, and the other horizontal line called conduction band. Valence band, conduction band. And horizontal axis is actually real space. X, Y, Z, whatever you want to call. So in the case of ideal semiconductors, we don't have any carriers. We don't have any carriers at 0 temperature. At 0 temperature, all electrons are forming bonds. Okay? But at elevated temperature, statistically, such bonds are broken. Statistically, such bonds are broken. At very elevated temperature, of course, they are all broken. Okay? So let's just say in the real space, if I have silicon crystal like this, and somewhere, if the electron is removed, so that there's actually freely moving electron somewhere, because there's freely moving holes somewhere, there's hole and electron, then what we draw here is that, okay, electron is here, so freely moving electrons in this coordinate somewhere here. And then hole is here, so there's actually empty holes. Electrons and holes are here, okay? And if there's more, then we can actually make more. Now, as you know, group 4, part of the periodic table, looks like this. Germanium. And then we have nitrogen, phosphorus, arsenic, antimony, bismuth in group 5. And we have here boron, group 3. Okay, so the trick is that to increase the conductivity of silicon, there are two things we can do. One is to increase conductivity. We can replace silicon with donors, that is usually phosphorus, arsenic, antimony, and so on, or acceptors, boron, aluminum, gallium, etc. So this is group 4. This is group 4. group 5, sorry, and this is group 3. The reason is that I can replace one of the silicon with phosphorus. Okay, and if I replace one of the silicon with phosphorus, phosphorus has 5 valence electrons rather than 4. So there's one extra electron. One extra electron is introduced. Okay? And this electron binding energy to phosphorus is very small compared to binding energy of silicon and silicon, covalent bonds. So in fact, as you know, as I said, binding energy, silicon binding energy is in fact energy gap, and that is, in the case of silicon, is 1.1 electron volts. 1.1 electron volts. Binding energy of electron to phosphorus is in fact about phosphorus plus electron minus binding energy, which is basically donor energy, is about 50 milli electron volts. So this is factor of 20, roughly, larger, right? The electron binds to phosphorus via Coulombic energy. Phosphorus is positive, electron is minus, so it's a simple, pure Coulombic energy. And silicon-silicon bonds are basically covalent bonding, so it's much stronger. Okay? So, if I take the conduction band as a reference for freely moving electron, then this electron binding energy is only 50 millielectron volts, or 0.05 electron volts below the conduction band, right? The trap depth. This is a freely moving electron level. And there's a trap at the site of phosphorus, which is only, trap, if you will. This is like, there's a trap where the phosphorus is. And this is only 50 millielectron volt deep, right? So usually we just draw one line. If I introduce phosphorus, I introduce extra electron at the position of phosphorus. But if the energy is large enough, then such electrons are excited to conduction band, and this phosphorus level becomes empty. Make sense? So now this electron, excited means if I cut the electron here, right? The thermal energy provides enough energy to cut electron here so that this electron can move around freely, while phosphorus is left alone, positively charged. So this is positively charged, right? But this positively charged phosphorus cannot move around. Okay, and if this positive phosphorus can move around, then that's, that can actually transfer charge. But phosphorus is stuck there. So phosphorus cannot move. So there's only one extra electron. So there are two electrons, one hole. Well, this electron and hole were created by breaking silicon bonds. And here, this electron is provided from phosphorus. And they're freely moving. Okay? Likewise, we can actually replace one of the silicon with group 3 acceptors. So if I replace one of the silicon with boron, then one electron is missing. Okay? One electron is missing, so I actually create one hole. One hole. Okay? And this hole is like just like quasi-particle. It's like electron, but it's a different opposite charge. And this hole is bound to boron by Coulombic energy. But it's just the opposite charge, right? Opposite charge. And this binding energy is also about 50 millielectron volts. This binding energy, again, is very, 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 very weak compared to band gap. So, to draw such level, when I introduce boron acceptor, I draw a line here, okay? Because boron is here, so I just draw boron just above here. And this contains one open circle, which is whole. And this energy is roughly 50 millielectron volts. This is an acceptor ionization energy. Okay? So boron minus hole plus acceptor ionization energy, roughly 50 millielectron volts. Why do I draw open circle here? Because just in general, I'm drawing an open circle as a whole and field circle as an electron here. Because this valence band is filled with electrons, right? Black dots, filled with electrons. And then this hole is empty, so if I bring one of the electron from here to here, I will kill such hole. And instead, I create hole here. So I can just see opposite way, hole is excited from here to here. When I break the bonds of hole between hole and boron, then once this is broken, hole can move around freely. Okay? And electron, once hole is missing, boron remains negatively charged so that boron becomes negatively charged just sitting here. And new hole is created. New hole is created. And holes move around with effective mass of holes. So what I'm trying to say here is that in this direction, energy of electrons higher. Right? Energy of electrons larger in this direction. However, energy of hole is larger in opposite direction because it's an opposite charge. So for hole sitting here is lower energy than hole sitting here. Hole sitting here is hole bound to boron. And so it has a trap of about 50 millielectron volts deep. This is lower energy for hole. And when hole is trapped here, boron, basically this is equivalent to boron trapping hole. But then if hole can be excited to this valence band and become freely moving particle. Okay? And we call it ionization energy because once hole is excited to valence band, the remaining boron becomes negatively charged. It's ionized. So this is why we call it donor ionization energy or acceptor ionization energy. Okay. The next, I am drawing all these electrons sitting in the same energy level. This is just out of convenience or, out of custom. In fact, electrons moving around takes energy different from one another. Okay? We don't draw like this, usually. We always draw, electrons here, here, and there. But the fact is that electrons actually takes different energy in the band. That's obvious, right? Because that's obvious. That's obvious because here, first electron takes the minimum of the conduction band. The next electron takes slightly larger level. Next electron takes slightly higher energy because they are completely dispersed. Okay? So they don't take exactly the same energy. So how do we account for such effect? To account for such effect, we introduce the concept of the density of states, Fermi function, etc. So basically, the situation looks as follows. If I draw conduction band, valence band, okay, this is in real space. Now I'm going to draw a conduction band, and this is density of states for valence band. And density of states for the conduction band looks like this, and density of states for valence band looks like this. Okay? As a function of energy. And in fact, this goes with energy minus EC. Here's EC, here's EV, 1/2. Okay, it grows as 1/2. And this goes EV minus E 1/2. So actual energy. So this shows how densely packed, how for example, how seats in a stadium are arranged. You go to World Cup football, and there's always this sort of seats on the stadium. Maybe at the bottom of the stadium, there are only 2 seats. But at a little higher level, there are 4 seats. Even next level, there are 5 seats and so on. So there are seating distributions as a function of the energy. Okay? If electrons are bosons, Bose particles, we can put seats all at the very front row. But because electrons are fermion, there's always an excursion principle, and then therefore we have, we have electrons with different energy, which actually forces us to arrange seats for electrons as a function of energy. And number of seats as a function of energy grows like this. So at the bottom, there's a very small number. As we go up in the stadium, we get more and more seats at somewhat similar energy, for the same energy. Okay. To be more precise, this is number of seats or states per delta E. Delta E. So in a small unit energy, we count how many number of states we have. And again, each state has different energies, but we count the number of states per delta unit energy difference. So we know the seeds distribution now. This is density states for three dimensions. So density of states for 2 dimensions is different, and density of states for 1-dimensional crystal is different. This is density of states for 3-dimensional crystal. How we distribute electrons or holes among seeds depend on the Fermi level. Okay? So how do we define the Fermi level? Okay, let us just define the Fermi function. So as a function of energy, let's define Fermi function. Fermi function. How should I say? Yeah, Fe. Let's just say Fe. F, which depends on E. In this book, they use actually F, E. Okay? And this depends on the Fermi level. So let's assume Fermi level is exactly at the center of valence band and conduction band. So this is a Fermi level. And Fermi function is something like 1 plus exponential E minus EC. Let me draw. This is too tight. But Fermi function is actually given in the book. So let me just draw Fermi function graphically. So I'm going to draw a Fermi function for 0 temperature. Fermi function for 0 temperature looks like this. This is 0 and 1. Okay? So, and Fermi function provides the probability that you find electrons. So, in this energy range, probability of finding electron is 0. And here, probability of finding electron is 1. Okay? In fact, Fermi level is defined where Fermi function EF is where 1/2. So Fermi level by definition is where the probability of finding electron is 1/2. Probability of finding electrons 1/2. It's all 0 here, it's all 1 here, and Fermi level there's a jump, but it's basically 1/2. At higher temperature, for temperature equals to 0 Kelvin. At higher temperature, Fermi function becomes smeared out. Becomes even more smeared out. Becomes even more smeared out as temperature becomes larger. Larger temperature. Okay? So what this means is that by increasing the temperature, we increase the probability of finding electrons at higher and higher energy. Okay? And this part is probability of missing electrons. What is the probability of missing electrons? It's the probability of finding holes. Right? Probability of missing electrons is that probability of finding holes. So basically, this actually shows, this difference here shows how how much holes we find, how probable it is to find holes. Okay? So at the end, the probability of, so at the end, here I'm going to show n, concentration of electrons, concentration of electrons, concentration of electrons. Here I show P, concentration of holes, okay, holes. And then that is given by seed distribution times probability of finding electrons. There are seeds. We know seed distribution. Now we have to know, then we also know how probable it is to find electrons. So simply seed distribution times probability of finding electron actually is concentration. So G E times FE equals NE. Right? Make sense? And that is given by for this particular temperature, for this particular temperature, for this particular temperature, for this particular temperature, for T1, whatever the temperature this is. For T1, this blue times white is something looked like this. Right? This blue times this white, this part, this part. Looks like this. Right? So whole electron concentration looks like this. Because seed times probability of finding electrons at such seed distribution. And probability of finding hole also looks like this. Because hole seeding times actually P is given by, PE is given by G, this is GC, so this is G valence band energy. So P whole concentration given by G sub valence band E energy times 1 over FE. Probability of finding electron, 1 minus FE is probability of finding holes. And that is this red curve. So this is why I said, okay, look, electrons are not necessarily taking the same energy. In fact, in the conduction band, electrons within conduction band, electron takes different energy. Freely moving electrons. Freely moving holes take different energy. Okay? And this is the intrinsic semiconductor case. Intrinsic means no impurities, just simple silicon only. Therefore, therefore N equals to P. Concentration of electrons and concentration of holes. Basically this area and this area is the same. Okay? Well, obviously that has to be the case because when there's no impurities, with no donors, no acceptors, we always create one electron with one hole. One electron with one hole. So always the number of electrons and holes are numbers of electron, and it's the same as number of holes. Okay? And that is guaranteed by placing Fermi level in the middle. If I put donors, then, as you know, I create more energy levels here. Right? If I put more and more phosphorus. Okay? And at low temperature, all temperature close to 0 Kelvin, electrons are all captured by each phosphorus. So here's, each electron is trapped by each phosphorus. Where's the Fermi level? Here, valence band is filled with electron. So here, probability of electron is 1. Finding electron is 1. Even here, at this energy, probability of finding electron is 1. At this next state here, the conduction band, probability of finding electron is 0. Right? Because there's no electron. So, in this case, Fermi level is somewhere between here. Okay? If I excite half of the, at elevator temperature, if half of the phosphorus is empty, so we have 3 out of 6 phosphorus being empty, and 3 phosphorus being filled with electrons, then probability of finding one half is exactly at this energy level, right? Because we have phosphorus. Not exactly because we have more electrons here. So it's a little bit between, but mathematically you can define exact position of the Fermi level, but conceptually, this is how you see, okay, Fermi level is somewhere close to the donor level. In the case of phosphorus doped silicon. So what happened if you actually move the Fermi level to the donor level, close to the donor level? What happened? We are going to shift in this diagram Fermi level close to the conduction band. Fermi level now is shifted, and the whole curve is shifted. So this curve is shifted by this much, so it's going to be shifted like this, right? This is shifted to Fermi level here, okay? Because Fermi level is now close to the conduction band. And in this case, this becomes larger, and this becomes much smaller. Because this times white is this times this white is this. So for the case of N-type semiconductor, and likewise, we're using the same argument. In the case of acceptor doped semiconductors, we have all these holes here. And in this case, Fermi level is somewhere here. Electron here, empty electrons here. So Fermi level is close to acceptor level. Therefore, in this case, Fermi level is shifted to somewhere here, close to the valence band, right? Fermi level is close to the valence band, so that this white line is shifted like this. Now it's parallel, but it's shifted like this. This is an intrinsic case. This is a donor. So Fermi level, Fermi function, this is N-type. This is P-type. In the case of P-type, this becomes large, and this becomes small. So by introducing donors, phosphorus, we can introduce more electrons. By introducing acceptors, we can introduce more holes in the conduction band. However, as you can see, because Fermi function is exponential function, it is impossible to just create electrons only. There's always this small tail that creates holes in n-type semiconductors. So this is called majority carriers. This is called minority carriers. Okay? So this is majority carriers in n-type semiconductors. Majority. And this is minority. Okay, but in any case, so there's always minority carriers. Okay. And that becomes important when it comes to device physics, device performance. Okay, so I have successfully, hopefully, introduced the concept of concentration of carriers, concept of extensive states, concept of donors, concept of acceptors, and so on. And that actually covers most of chapter 1 and 2. And you can read the book for equations and so on. But the concept is not shown so specifically in the book. So hopefully that actually is sufficient for you to work on problems.